Welcome everyone to this morning short course. I will share the material. I will share my screen first. Let me see. Okay. Yes. Now everybody could see? Adela?
Yes, your screen is visible, madam.
Okay, thank you.
You're welcome.
Okay. Yes. Now, okay, what am Adela, I just would like to have a confirmation from you. Until what time am I supposed to give my short course, give the course?
Your lecture is until 10:30, miss.
10:30. Does that include question time?
Uh, it will include question and answer session.
Okay, okay. Okay, my topic this morning is about outstanding claims liability in earthquake insurance. It's an application of a non-life insurance. So I would like to start by explaining to all of you. Most of you probably already know about this, but probably some of you have not. What is actual science? Actual science is actually a branch of knowledge which applies mathematics, probability theory, and statistics, economics, finance, and computation in assessing risks of financial losses due to measurable non-preventive events. So it's only applicable to measure measurable non-prevented events or to model measurable non-prevented events. Such events are those which will occur at a certain time in the future with probabilities greater than 0. But, however, the time of the occurrences of the events and the corresponding amount of the financial losses cannot be determined with certainty at the time of valuation. Now, actual science may be applied in life insurance, in general insurance or non-life insurance, including reinsurance. Now, non-life insurance are all insurance business except life insurance business. And actual science can also be applied in pension fund, investment, as well as other risk management, and lately in data analytics. Okay, what is the outline of the lecture for this morning? These are the outlines. I would like to explain briefly what is the nature of natural catastrophic events, such as the catastrophe events such as earthquake, landslide, hurricane, okay, or tsunami, okay. But basically in this lecture, I will focus on earthquake. And then I will also explain briefly of what is earthquake insurance. So it's not going to explain the whole idea or the whole business of earthquake insurance, but I'm only going to explain just a little bit, particularly characteristics of the claims in earthquake insurance business. And then I will explain also what is outstanding claims liability. And probably some of you already know or heard about runoff triangle methodologies, in particular chain ladder method. And then earthquake catastrophe model, what is the CAT model for earthquake? Also explain the last module in the earthquake CAT model is the loss module. I will explain a little bit about what is the probable maximum loss is. And how do you determine the outstanding claim reserve? As you may see in here, I mentioned two terms here, outstanding claims liability, and then there's outstanding claims reserve. Actually, these two things are very different, but in this lecture, I will use this term interchangeably, okay? So reserve and liability is not actually the same in practice. I will also give examples of what our heavy-tailed distributions are, and also we'll give you example the importance of modeling your data correctly because depending on what distributions your data, the distributions of your data, the value at risk or the conditional tail expectations or other risk measures may be different significantly. So it's really important to have a correct data in the first place, and then to model the data correctly in order for you to measure the risk of your data, in particular your claims data. And then I will also just briefly explain what earthquake catastrophe reserve is and what's the regulations, in particular in Indonesia by Otoritas Jasa Keuangan, OJK, and the importance of having an in-house actuary within an insurance company, in particular insurance company which sell earthquake insurance product, or moreover in reinsurance company. Okay, nature of natural catastrophic events. These are three basic nature of natural catastrophic events. The first one is that the time when it occurs, the frequency and severity resulting of the natural catastrophic events are actually random variables. Now, those who already studied statistics, especially probability theory, know what the definitions of random variables are. The second is that the events, for instance, earthquake, will result in, for instance, claim severity, which is high, but then the frequency is very low, meaning that the occurrence of earthquake is very rare, hopefully. However, when it occurred, it will give a very devastating impact, not just loss of lives, but in terms of claims, financial losses, it will be severe or very high. And then the third is that the distribution of the aggregate financial loss or compound model of the financial loss in a particular period are heavy-tailed. Now, what is a heavy-tailed distribution? A heavy-tailed distribution is actually a skewed distribution. The shape of the distribution is skewed with the tail is to the right, okay? Where it means that you still have large claims amount with probabilities which is quite large, not very large, but quite large compared to those distributions which is categorized as light tail. For instance, an absolute light tail distribution is an exponential distribution. Okay, so some of you probably already know what a compound model is. A compound model is actually the sum of the amount of claims random variables, but you sum them with a frequency which is following a distribution. For instance, in a compound model or a collective model, you have the primary distribution, a Poisson distribution, whereas the secondary distribution is, for instance, a log normal or a gamma or a Pareto or other right skewed distributions. Okay, this is a map of Indonesia. Okay, it's an archipelago, largest archipelago in the world, where the Indonesian archipelago, the Indonesian archipelago, is surrounded by three large tectonic plates, and this area here are actually very prone to earthquakes. It's called the Ring of Fire. Okay, now the three tectonic plates surrounding Indonesia, here is the Eurasia plate, here is the Pacific plate, and here is the Indo-Australia plate. So Indonesia is actually in the meeting of these three tectonic plates, which makes it prone to earthquakes. Now, Indonesia can be divided into these many megathrust. We see here there's a Sumatran megathrust, where the segment megathrust are these, and then the Sunda Strait megathrust, and then the Java megathrust, Banda megathrust, Northern Sulawesi thrust, and Philippine thrust. So M1 up to M16, and these are the segments of each of the megatrusts. Okay, and you could find this map in this resource. Okay, why did I put this map here? It will give us an idea of how important it is to manage risks, not just the risk of losses of lives in Indonesia caused by earthquakes, but also the financial loss because of the catastrophe event. Okay. Now, what is earthquake insurance? The earthquake insurance is actually a long-tailed business. What does it mean by a long-tailed business? Now, it's different by the term heavy-tailed, okay? Heavy-tailed is totally different than long-tailed. Long-tailed business is actually an insurance business in which since the time an event occur which result in claims, up to the time or period that the claims are settled will take longer than 1 year. Okay, for instance, if an earthquake occur at a particular area at a particular time, let's say in December, past experience, December 2005, for instance, where we had that big earthquake in Aceh, which resulted in devastated area caused by a very large tsunami. Now, when it occurred, not directly any claims of financial losses are reported, okay, to insurance companies. So there is a delay between the occurrence of an event to the reporting of financial losses or claims occurred. There is a delay. And then after the claims is reported to an insurance company, it will take time also for the insurance company to investigate how much actually the cost of the claims, or how large is the claim. So investigation need to be carried out, investigating the area, whether the reported claims is actually the actual claims suffered by the policyholders. So there is another delay, but then also after the investigation, after the claims is approved, then there is another delay up to the settlement for the whole amount of claims. So normally the claims will be paid in installments, but until it's really finalized, it will take more than 1 year. Moreover, if it's reinsurance companies, covering insurance companies which cover insurance, earthquakes insurance, so it will take a lot longer. It could, the whole claims from all the seeding companies may take like 5 years or 7 years to be finalized. So there is a delay between occurrence of the event and the reporting of a claim. And then there's another delay between the time of reporting and the settlement of the claims. And then another reason why it may take longer than 1 year, probably sometimes it could, for a long tail business, not just in earthquake insurance, for other long tail business insurance, then a closed claim might be reopened, and then additional money may need to be paid. Now, as opposed to long tail business, our short tail businesses. For instance, in non-life insurance, health insurance, as well as automobile insurance are short tail business. Because since the claim occurred up to the claim is finalized, it will take a lot less than 1 year. For instance, if all the paperwork is ready, then an insurance company need to pay and the whole claim reported by the policyholder. And with health insurance or car insurance, at the most is 1 month after all the paperwork is ready and approved. So we need to obtain an appropriate probability model to model the loss or claims data of the earthquake insurance in order to determine the pure premium. Now, what is the pure premium? It is the expected value or the mean of the distribution of losses or claims. So that's why we need to have a clean and valid data in the first place for the severity of claims as well as the frequency of claims in order for us to appropriately determine a probability model to the data. Because the pure premium is actually the expected value of the distribution of loss or claims. Then, after we obtain the pure premium, we add loadings to the pure premium, and that's the risk premium, which is actually charged to the policyholder. Now, we need an insurance company also need to determine or set up appropriate technical reserves. Now, not just the premium, but the insurance company also need to determine a correct amount of technical reserves. The first one of the technical reserve is the unearned premium, and the other one, which is very difficult to determine, is the outstanding claims reserve. Now, not just long tail insurance businesses that need to determine the technical reserves, but all insurance businesses. However, in a long tail insurance business, determining the outstanding claims reserve is a bit more difficult or complex. Now, how to determine the premium? This is what I mentioned before. The risk-adjusted premium or the risk premium or the risk which is or the premium which is charged to the policyholder is actually the pure premium, which is the expected value of the distributions of claims or losses plus loadings. Now, what are those included in loadings? Those included in loadings are such as the operational cost of the insurance company, also commission to agents or brokers, and also cost of claims such as paying an independent party such as adjuster to investigate if a claim is reported, and other, for instance, also you may put in the loadings are profits that you would like to expect. So you probably would like to put that in loadings as well. So this is another thing in actual science. It's not just how to determine the pure premium, but also how to put the loadings appropriately, because if it's too much or too high, then the risk premium will be a lot higher, probably compared to other premiums charged by other insurance companies. So the competition will be very fierce then. But if it's too low, then you may not have enough premium reserve, unearned premium reserve, if you later on have claims reported. So determining the proper value of loadings also include the management of the companies, because you also would like to know the assets of the companies in order to compete with other insurance companies. Now, this is what I meant by, so in insurance business, first of all, actuaries need to determine the right amount of premium, which is the risk adjusted or the risk premium, but also how to determine the outstanding claims reserve. Now, the outstanding claim reserve meaning that once a claim is reported, it's not directly being paid. As I mentioned before, there are delays. So that means there are claims which are still outstanding, need to be paid by the insurance companies, but are not paid yet, are not finalized. So insurance company need to put or set aside an amount of money for these outstanding claims. Now, sometimes it's also called the outstanding claims liability. Now, what is a liability? Liability is different compared to those as reserve, because when you determine a reserve, there are other things need to be considered. But in order to determine the liability, you only look at the past claims data, whether frequency or severity. So I'd like also at this point to explain to you what a runoff triangle is. Remember when I mentioned before, for a long-tailed business, there is a delay between the occurrence of an event, for instance, an earthquake, and the reporting of the claim caused by that event. And then there's another delay between the time after it's being reported and the time that the claims are settled. So these will take time. Now, if a reinsurance company, for instance, will have many ceding companies, and the ceding companies may sell earthquake insurance business. So when an earthquake occurs at a particular area, for instance, in Indonesia, then there is there is a delay between the insurance company to report the claims caused by a particular earthquake to the reinsurance company. Okay, so because of those delay until it's being paid, the whole claims are settled, it may take more than 1 year. So let's look at what is a runoff triangle. Here we have a row which is called the accident period or the accident year, and then we have a column here which is called the development period or the development year. Okay, now this CIJ is the cumulative paid or the cumulative incurred claim severity. Sometimes these cells could also be filled by claims frequency, not just severity. Let's say now we have claim severity in each of these cells. Now you may see here there is two parts of this triangle. Sorry, there's this part of this diagram, which is the upper part of the triangle and the lower part. Okay, so this is the upper triangle and this is the lower triangle. So the rectangle here consists of these two. Now the gray area here is actually the amount of claims that you need to estimate. So let me explain how this data of claim severity or claim frequency are recorded. Okay, now the accident period is, for instance, accident year is the year in which an earthquake occur, for instance. Okay, so this is in year 1, in year 2, up to year N. And the development period is actually how the claims are paid. The development of the claims are paid. For instance, we also have one 2 up to n here. You can see here that the number of accident periods and the number of development periods are equal, but it may not be the case in some cases. You could have the number of development periods is less than the number of accident period, and you would like to have that to have the number of development periods to be less than the accident period. You don't want this to be a lot longer than, for instance, 5 years or 7 years. But sometimes with certain business, it could take up to 10 years. Okay. So what does this mean? This is the cumulative severity, claim severity, for instance. Now, let's say accident year 1 is, let's say, year 1980, year 2001, for instance, year 2001. So C11 is actually the amount of claim paid in the same year as 2001. Okay, so development year 1 meaning the claims paid in the same year as the incident occur. Okay, now this is the total of all incidents occurring in year 1, of all incidents, for instance, earthquakes or other natural catastrophe occurring in year 1. These amounts C11 are those amount of claims out of those occurring in year 1 paid in the same year. Now, there are also claims occurring in year 1 which are not paid in the same year. It may be paid in the second year. Not same year, but probably the next year after it occurred. So you add C11 with those claims which occurred here but paid 1 year later. So this is the cumulative here. And then probably there are also claims occurring in the first year which are not paid in the same year, neither it was paid in the year after, but it is paid 2 years after that. So you accumulate from those claims paid in the same year, the next 1 year, and the next 2 years in this cell, and so forth up to, let's say, if the incidents occur in the first year, then all claims will be paid or finalized or settled after, let's say, n equals 10, so 10 years. So this is actually is called the ultimate claims, the total claims caused by the incidents occurring in the first year. Okay. Now, there are other incidents occurring, let's say, in year 2. Let's say this, if this is 2001, this is 2002. So out of those incidents which occur in 2002, for instance, this much claims are paid in the same year as this. See here, development year 1, meaning the same year as each of this accident period. So C21 is the amount of claims caused by an incident occurring in accident year 2 and are paid in the same year as the accident year 2. Okay, so let's say there is other claims which are occurring in accident year 2, which are not paid in the same year as accident year 2, but is paid late 1 year later. And if you add this plus those claims that is being paid a year after it occurred, it's C22. So these are all cumulative claims. Now, besides, and you continue up to year 10. So year 1, 2, for instance, if year 1 is 2001, now this is 2010. So besides the row and the column, you also have the diagonal here, the diagonal up to here. Okay. Now, there is an assumption here. If, now this is the problem with a run of triangle. There is an assumption that if all claims are settled within n years, let's say 10 years, then in the accident period 2, these claims will be also settled in 10 years time. So that means because we only are at this stage, this is actually the diagonal is actually the current year, okay, or paid to date year, or the payment year, the last payment year. That means we don't have the amount, the whole amount to be paid when we arrived here. We still have to estimate what is the amount here, which is the ultimate claims. This is for accident year 2, this is for accident year, sorry, this is for accident year 1, this is for accident year 2, and so forth. So what we want is what is the value here, okay? Now, as I said before, these are cumulative payment. So the last diagonal here is actually the last year of payment. So if we add one more year here, then with the run of triangle assumption, it means that it will take you a lot longer than 10 years, but 11 years, for instance, to finalize the claim. However, you may not have a perfect triangle like this for the observed values. You might have like a trapezium. Trapezium, let's say, even though we record the data further, accident years n+1 and so forth, but it will only take n years to finalize. So we will have a trapezium here, okay? Now, these are called, this is what is called recording claims data in a runoff triangle format, okay? So the observed values are these in the upper triangle or the upper part of the rectangle, okay? Now, we would like to estimate those values here in the lower triangle. Okay, there are so many methodologies to model claims experience in a long-tailed insurance business, and also to estimate the outstanding claims liability. Now, those methodologies may be deterministic, and what we would like is probabilistics, okay? Now, the chain ladder method is the most used one. It is simple and it is deterministic or distribution free. So we have data recorded in a runoff triangle format like this. So there are so many methodologies. One method is called chain ladder method, is the most used one. However, there are assumptions underlying this method which need to be met by the data, okay? So it's important with any methodology that we use in any statistical analysis, we need to check whether the assumptions underlying the model or method we use are not violated by the data that we want to model. Unfortunately, with earthquake insurance, the claims data, the historical claims data, normally will cause the assumptions of the chain ladder method are not met, okay? So it's almost surely that we cannot use chain ladder method to estimate the outstanding claims liability of earthquake insurance business, okay? Now, what is a chain ladder method? I gave a lot of references at the back. I will show you some, okay, which you can read later on regarding chain ladder method. For instance, paper by Mac, this one here. This is a very good start for you to understand what a chain ladder method is, okay, by Mac. And then Mac also wrote other papers using different triangle method, which is called Bornhueter-Ferguson, which is good to be used when your data is scarce, okay? and you can find this in the Casualty Actuarial Society website. Okay, and this one is also, you could find it in the actual Casualty Actuarial Society website, Aston Bulletin. So this is a very good first paper if you would like to learn more about what is a chain ladder method is. Okay, now I am not going to go in detail in how the method, on how to calculate the outstanding claims liability using a chain ladder method, because you could read this explanation here. There are so many symbols. You could read here these notes as well as the paper that I showed you, paper by Mac, 1993. But I'd like to pinpoint here. If we have time later on, I will explain about the methodology. Now, there are basically three assumptions underlying the chain ladder method. The first one, which is actually could not happen in a catastrophe insurance. For instance, earthquake or hurricane or tsunami. Okay, the first assumption is that patterns in the claims activities in the past will continue to be seen in the future. So whatever the patterns are in the historical claims, it will continue up to the future. Okay, now if you want to use this assumption for short tail businesses, for instance, just would like to know how you can estimate the claims for car insurance or health insurance, even though it's not a long tail business, you can change the accident period by quarterly, for instance. So you only have 4 here. Okay, so quarter 1, quarter 2, quarter 3, and quarter 4. But then you could see, you know, how many years you have already past data of your business here. Okay, so you have to have too long of development period for short tail businesses such as car insurance or health insurance. You could use also these methods. Now, however, you have to check first whether these assumptions are met by the data. Okay, first one, patterns in the claim activities in the past are will continue same pattern in the future. And then claims between accident years are independent. So what it means is that these here claims in the development year 1, C11, the incremental claims basically. So you don't look at the cumulative claims, but incremental claims, meaning the incremental claims in development year 2 is the C12 minus C11. The incremental claims in development year 2 is C22 minus C21, and so forth, up to the incremental claim in year end, development year end, is this value minus that value. Okay, so when you look at the incremental claims, now between these claims are independent, these claims are independent, these claims are independent. Okay, so claims between accident years are independent. Yeah, sorry, yeah, oops, where am I? Okay, here. And then for a development year, claims experience are stable across accident years. Now, we will look later on in the formula, what does this mean? Meaning like this, if you want to apply a chain ladder method, so if we have a runoff triangle of cumulative claims, either incurred claims or paid claims for severity of claims, or even claims for frequency, either incurred claims frequency, for instance, or paid claims frequency, for instance. Now, if we look here, we would like to have, let's say, the movement of the development of the payment from development period 1 to period 2 is similar for each of the accident years. Okay, so the pattern is, let's say, if C12 is, for instance, 3 times C11, then we would like C22 almost 3 times C21, and so forth. So also from development period 2 to development period 3, for instance, if C13 is actually, let's say, 1.7 times C12, then we would like here is also approximately 1.72 times C22, and so forth. So, however, that assumption is very difficult to be met by many of earthquake insurance business. Okay, so if, let's say, for the movement of development payment from development year 1 to development year 2, or age to age factor, what is called sometimes in many papers, scientific journals or scientific papers. So we could say that from development year 1 to development year 2, the factor of payment is on average, let's say, from here to here, on average, let's say it's 3.2 times. So these values here on average is like 3.2 times these values here. And that continues. For instance, if we hope that by N years, all the claims occurred in this year already being paid, so the ratio between this and this is 1. Okay, so there is this assumption for chain ladder method, okay, which is the claim experience are stable for a particular development year. Now, another characteristic of a chain ladder method is that the chain ladder method will give an estimate of the outstanding claims liability, which is a point estimate. What is the amount of the outstanding claims liability? That's it. Okay, we do not have the measurement for the uncertainty of the estimate. However, paper by Mac here also gives you a distribution-free formula to calculate the standard error of the estimator of the outstanding claims liability. So at least if you don't have the distribution for each cells of these claims, aggregate claims, at least you have what is the estimate of the reserve or outstanding claims liability, as well as the standard error or the uncertainty of that estimator. Okay, so it's important to also measure the uncertainty of your estimate. Another problem with the chain ladder method is that it is really sensitive if there are variations, large variations in the data, because of this assumption here, in particular, that claims experience are stable across accident years for a particular development year. So if there are variations in the data, and then you will have a problem in using chain ladder method. In earthquake insurance, normally if let's say a big earthquake occur, so probably one cell here in development year 1 will have a value of 0, because let's say in that same year, let's say the earthquake occurs in December. So of course we could not expect that in the same month the claims is reported or is being at least reported in the same year, because it's already the last month of a year. So we may have some cells in the first development period here equals to 0. Some cells, not all, hopefully. Okay. And also with earthquake insurance, the incremental claims, incremental meaning not the cumulative, right? The not cumulative payment I've shown you before how to calculate the incremental payment. For instance, incremental payment here is just this value minus that. Incremental payments in here is just that value, the cumulative here minus that. Incremental here is just that cumulative minus that, and so forth. Yeah, the development period before that development period, and so forth. So you may have some cells here in here. You may not. So that's why the chain ladder method will be largely affected if there are large variations in your data. Okay, now these are assumptions written in mathematics formula, which I mentioned here. So you could see what the assumptions are. I'm not going to spend too much time now here. We could go back here again if we have some more time. But you may look at this again and look at the paper by Mack 1993 in order for you to understand the calculation. And then you could check your understanding by calculating the examples here. You could check. Now, these what I call the development factor, okay? Now, and these are the total reserve, the total outstanding claims based on this data here, okay? You can check later on when you have time. I will go back here if we have more time. Okay, I'd like to explain about catastrophe model. Now, in a catastrophe model, there are 4 modules, okay? And let's say this is a catastrophe model for earthquake events. There are 4 modules here. The first one is called hazard module. And the second one is inventory module. And based on the output of the hazard module as well as the inventory module, you have a vulnerability module. And from here, you have a module which measure financial losses caused by all earthquakes occurring here, suffered by all, let's say, buildings, which is recorded here. And these are the vulnerability, how big or how large or how much financial losses caused by the damage of buildings caused by an earthquake, for example. Okay, now the earthquake here, sorry, there is information missing here. If you could also check or write down in your notes. Basically, this is the earthquake moment magnitude, distance between the building, for instance, and the epicenter of the earthquake. And then the third one is the soil type where your building, for example, is being built, okay, or located. So there are 3 here, actually. So I'm sorry because I didn't realize that some of the information are missing in the PowerPoint. Okay, so 3 things: earthquake moment magnitude, distance between whatever building or infrastructure that you are insuring, you want to be covered by the insurance company, and the epicenter of the earthquake or the source of the earthquake. And the third one is the type of soil where your building is located. Okay, so you input this to the hazard module, and then from here and from the inventory of all the buildings that you covered, you also measure how big is the damage caused by the particular earthquakes, and then you could calculate how much financial losses. However, I would like to say this. This is a very big model, okay? So one person or one expertise cannot do this. In building this model, you need people with so many expertise. You need seismologists, you need geophysicists, you need, and if you cover also not earthquake insurance, but also hurricane, you need meteorologists. You need also mathematicians, statisticians, actuaries, you need computer programmer, probably later on data analyst. So one person cannot do this, one profession cannot do this, okay? And with this, you have to inventorize all the coverage that you want to cover, buildings, whether commercial or residential, whether it's agriculture. So you have to inventorize. And then here is a very big modeling itself, not to mention here, okay? You need seismologists, you need physicist here, okay? If it's earthquake insurance, you need meteorologist here. If it's hurricane, and then you also need mathematicians if you want to model tsunami, okay? So these catastrophe models are different depending on what natural catastrophes that you want to model. So CAT model for earthquake insurance is different from CAT model for let's say floods, different than hurricanes, different than tsunamis, okay? So here in the end, you will have to model the loss, let's say, following a particular distribution. So again, this is a very big effort, cannot be done by only one expertise, okay? Now, in each model, there are assumptions. Oh, yes. In each model, there are assumptions. So it's very, very difficult, as in particular, to validate your data because there are so many assumptions here. Now, loss module is the last module in a CAT model, which this one here, okay? Accumulation of those uncertainties due to method model use, inventory, assumptions made. So here you have accumulation of all the assumptions that you made here, all the modeling that you made here. It will end up here, okay? So can you imagine you need to measure the uncertainty also for your loss or claims distribution here. Now, it is important to understand this. There is no way anybody could predict exactly when future earthquakes will occur and how big the moment magnitude will be of that earthquakes. Nobody can do this, okay? So CAT model may be able to build probability models for losses based on the hazard and the vulnerability models. But we cannot know exactly when an earthquake will occur, and if it occurs when, where, we don't know. But we may be able, in order to develop the loss event, we may be able to create a catalog of earthquakes events based on past earthquakes occurring in the past, or a synthetic, what is called a synthetic earthquake catalogs. Okay, so we may be able to develop the hazard module using synthetic earthquake events. Okay, now we need to use a CAT model to obtain initial estimates of losses. But we always need to develop and adjust the model, as well as updating and validating the inventory module and the claims data. Remember, the claims data are recorded using a runoff triangle, like this, okay? Whereas, and these are only recording claims that already occurred but maybe not reported yet, or claims that already being paid. It depends on what claims that you are recording there. Whereas here we are trying to estimate the distribution of loss caused by past earthquakes, and depending on where and what buildings or infrastructure that we are insuring in order for us to calculate how big the damage will cost. The damage caused by the natural catastrophe here. Okay, so we need to update and validate inventory model and also the claims data as time goes by. Okay, now developing a CAT model for an earthquake insurance business is a multidisciplinary effort. This is what I mentioned. Oh yeah, civil engineers, of course, you need civil engineers there. I forgot to mention that. Okay, so these are basically minimal expertise or disciplines if you want to build a CAT model for a particular natural catastrophe insurance business. Now, what is probable maximum loss? Now, in the loss module later on, you will calculate what is called event loss table. Now, if you read this book here, let me see which one here. Did I forget to mention? I hope not. Oops. Oh, here, sorry, Scotton, Chen Scotton. This book is really good, but I have to warn you, it's very, very, very thick, okay? And if you're an actuary, if you're a statistician, if you're a mathematician, you cannot understand this book unless you discuss it with a geophysicist, with a seismologist, okay? So you need to have people in your team which can also explain to you what this book is. So, but this is a very good book to understand about CAT model, okay? However, I have to warn you that some of the terms here may be similar to those terms that we know in statistics or in mathematics, statistics basically, statistics, but it may have different meanings. Or some things, the term here that have different names, but actually have similar meanings to a particular definition in statistics. So that's why you need to really understand, to try to learn to read this book if you want to learn about earthquake insurance, because this is actually earthquake engineering handbook. It's not earthquake insurance book, okay? But in order for you to understand, you may not be an expert. Of course, you cannot. Nobody can expert in all. You cannot be an expert in this. You cannot be an expert in that. You cannot, well, this one is an inventory. You don't have to be an expert in that. You may have someone else to do that. But you may not be an expert in here, nor in here. But at least you understand how the model works so that you can understand what does occur in this module. So you may be contributing in some part in building the hazard module. You may be contributing, if you have a mathematics or statistics or actual background, you may have a contribution in here, and of course, major contribution here, okay? If you have a background in actual science, statistics, but mathematics may not, but statistics, actual science, major contributions here, okay? So you don't have to understand the whole book of Scotton. I don't either, but it takes time to understand the CAT model in order for you to build or contribute in, basically, in the end, you want to model this one here, okay? But you may start if you are interested. Now, need to compare the results of the estimated loss from a CAT model, which is this one here, okay, produced by a CAT model. Compare it with what? Compare it with the estimate obtained by the runoff methodologies, runoff of incurred or paid claims. I explained to you briefly about chain ladder method, But actually, in these references, there is another method called the Bonhoeffer-Ferguson. Now, this is actually a good method if you have a scarce data, and also for the runoff triangle of claims data of insurance business, you may want to use this and calculate the prediction error. This is the estimation, and this is the prediction error. So these two paper, you need to read these two paper in order to understand the Bonhoeffer-Ferguson method. Or excuse me, you may use GLM, generalized linear model, to model or to estimate the outstanding claims liability. You may want to estimate these values here using GLM. However, you work with incremental data, not cumulative data. Okay, so generalized linear model you may apply also in each cell. So I recommend, if you would like to do like a final project later on, you might want to read about generalized linear models. This is a good, where is it? This is a good book to start with in learning what a GLM is. Another is, yeah, this one is also okay, good too. Oh, this book is good for learning about non-life actuarial models. Now, this book is really good of learning what is stochastic approach for determining the reserve for claims. By Wuthrich, okay? You may want to read these books. It includes also chain ladder method, Bonhoeffer-Ferguson method, GLM method. However, I have to warn you, this book is quite mathematical. So you need to understand also each terms very well in these books because it's very mathematical. Now, another book, this one here, I'm sure if you're from the actual department, you know what this book is. This is a very good book to have. At least you have to have this book if you want to work in non-life insurance business, okay? However, this book does not cover earthquake insurance business, as I said to you, okay? It does not cover, but you have to read at least this book first. You don't have to read all of them because it's very thick and you will get lost. You have to start somewhere, so discuss it with colleagues from geophysicists or seismologists where to start, okay? But this book, GLM, is really good also to learn about generalized linear modeling, how it can be used to estimate the outstanding claims liability. There are so many papers. In scientific journals which you can find and look at in order to find a proper model or methodology to estimate the outstanding claims using a runoff triangle. Okay. Now, no model is perfect, and we may not be able to obtain the right runoff model to predict future claims. However, when we use probability models, we may be able to measure the risk. Now, you need to know several risk measures. Two of them are the value at risk and the conditional tail expectation, or the tail value at risk, okay? At least you have to know two, and I will explain the differences of those risk measures in determining the reserve if you have different models, probability models for your data. Now, for a reinsurance company, it needs to know the characteristics of the ceding companies, okay? For example, the delays in reporting, incidents which will require the reinsurance company to pay the claims of the ceding companies. Now, how to determine the outstanding claims reserve? We may, for instance, want to analyze the individual claims. We may. However, because it's so difficult to analyze every individual claims. When I say difficult, it's not impossible, okay? When I say difficult, it doesn't mean that it's impossible. And there are some methodologies without using runoff triangles in analyzing individual claims to estimate the outstanding claims liability. However, if you are using a runoff triangle methodologies, then you might want to use the result from your CAT model, okay? And the probability models applied to the runoff triangle of past claims. Remember, chain ladder method does not, it's a distribution-free method. It does not assuming any probability models underlying the claims. However, there are papers that assuming that the claims are following a normal distribution in order using the chain ladder method. But of course, we know claims are not following a normal distributions. Now, runoff triangles record past experience in aggregate formats. It will give some ideas on the profile of past claims. Remember, one of the assumptions is that whatever pattern in your past claims experience, it will continue to the future, right? So when using a runoff triangle model, we need to determine the distribution of the outstanding claims. At least we need to determine the estimate of the outstanding claims and its prediction error. So if we do not assume any distribution following or underlying the ultimate claims, then we might just estimate what is the outstanding claims and then what is the prediction error of the estimator. At least these two values, the first moment and the second moment. However, if we have the distribution, we can also determine the 75th percentile or the value, the 0.75 quantile or the value at risk at a 0.75 significance value. So we can determine the value at risk or the tail value at risk, or another word for tail value at risk is conditional tail expectation, okay? If we have the distribution. Now, this is the challenge. How to connect the result from a CAT model, which is here, the result here, okay? How to connect the result here, okay? And the estimates of the outstanding claims liability, where we obtain from any runoff triangle methodologies, how to connect those two results in what? To set up an appropriate outstanding claims reserve. So I'm not using outstanding claims liability term anymore, but outstanding claims reserve, okay? Now, these are some examples. I will finish soon so that we at least have a 15-minute question time. These are examples of heavy tail distributions, okay? So we may not be able to do a diagnostic check whether our outstanding claims liability following a particular distribution. But we may assume, because the reason why is because when we make the estimate for the outstanding claims liability, we don't have the whole data yet, okay? So we may just assume and then later on validate. But it's hard to validate the data because a future earthquake may cause different severity losses compared to past earthquake experience. So it's not that easy. But let's say we just assume in order for us to determine how much that we will reserve for outstanding claims, okay? Now, let's say we want to model our outstanding claims reserve with a gamma, Weibull, Pareto, and log normal, as well as log logistic distribution, where the mean is the same, 75 million, and the standard deviation is 150 million, okay? However, with the same mean and same standard deviation, the distribution will have different parameters values, of course. That means it will have different risk measures. For instance, the value at risk and the conditional tail expectation. Okay. Now, why did I choose these two? Value at risk is quite simple and easy to understand. However, it's not coherent. The conditional tail expectation is a coherent risk measure, and it will be used in the future more often by banks and also non-banks investment companies or financial companies, okay? Non-bank financial companies. So let's say we want to measure the value, to determine the value at risk and the conditional tail expectation, or sometimes it's called TFAR, tail value at risk, with security levels or significant levels of 0.75 and 0.95. Okay, now here are the comparisons. If you model outstanding claims liability with a gamma distribution, now, the value at risk for security level 0.75 means like we are calculating the 75th percentile. Now, the gamma value for the gamma distribution, the value of the VAR is 78 point something million. Whereas if you model it with log logistic, the value at risk in 0.75 security level is 85.5 million. Okay, the Pareto is almost the same. However, if you calculate the 95th percentile, the difference is quite large here. Look at the gamma. The value at risk is about 364 million. Whereas the log logistic is 198 million, very different. Okay, now the conditional tail expectation is actually the average values of those claims greater than the FAR. Here you can also see, okay, with the 75th percentile, the value at risk is this one's quite large. Compared to this one is 258 million, and with log normal it's about 218 million, whereas log logistics about 172 million. And these are the conditional tail expectation for each of the gamma, Weibull, Pareto, log normal, and log logistic. So, which value will you choose as your outstanding claims reserve? Which value? If you assume gamma with alpha 0.5, the value at risk is this. But the conditional tail expectation is this. Do you want to reserve that much or that much? Okay, remember this value is not coherent. You can also read papers of what coherent means. Also, one of the books that I mentioned before, you could also learn what coherence means by Klugman or by Yunse. Okay, so how much? Because the thing is that if you put a large value as your reserve, then you have to set aside assets which will meet your liability, because you need to have equal assets and liability. And also with the risk-based capital measurement for solvency, OJK requires you to have an RBC of at least 120%, which means the ratio of your liability and your asset is 1.2. Okay, means that your asset to your liability, not your liability to your asset, your asset to your liability at least 120%, meaning your asset needs to be at least 1.2 times your liability. Okay, so if you have large liability here, and this is just one, the estimation of your outstanding claims liability is just one item in your liability side. There are other things as well, but that's the largest normally. So you have to have an asset of at least 1.2 times your liability, all your assets compared to all your liabilities. Okay, that's based capital. Okay, now there's this website which explains to you why, besides you have to set up premium reserve, claim reserve, you also need to set up catastrophe reserve, which is also stipulated in Surat Edaran OJK number 27 in 2017. Okay. Okay, this one is actually perusahaan reasuransi for reinsurance company, for insurance company, and for reinsurance company. Okay, so these are three different reserves: unearned premium reserve, claim reserve, and catastrophe reserve. And why do you need to determine catastrophe reserves? Yeah, underwriting gains should be retained by insurers in the event of future catastrophe losses. So all the profit that you get, you don't just distribute it as commissions to your directors or shareholders or employees, but you have to retain some of it for future catastrophe losses. Now, these reserves will have a stabilizing effect on insurance premium, of course. It will facilitate the ability of insurers to fund catastrophic losses and mitigate the exposure of insurance surplus to policyholders to large fluctuations resulting from such losses caused by the catastrophe events: earthquakes, floods, hurricane, tsunami, landslides, and so forth. Okay. Now, that's why it's important, if an insurance company have actuaries, those reinsurance company in particular, it sell earthquake or catastrophe insurance, it would be good to have an in-house actuary, because the actuary will be able to see the company's risk profiles, its history and characteristics. In-house actuary has direct access to the company's data and is able to check and recheck and validate the claims data as often as needed. An in-house actuary is able to discuss matters as often as needed with other departments in the company, such as claims department, CAT modeling department, finance, accounting, product development, underwriting, management, board of directors, board of commissioners. Okay, as I mentioned, these are useful references. These references, not all of them are used in today's lecture. I just put them in because they are useful. These are not all the references that you need to read. There are so many others, but I did not put it here. Okay, so these references are not exhaustive. Okay, now the hazard map that I showed you before, you could obtain it from this website. Okay, so this is also good, this book, Generalized Linear Models in Reserving Risks. Okay. Okay, that's all.